next Wednesday and Wednesday afterwards. I wanted to check with you if there's any major objections to having a night session. No major objections. Yeah?
It's then the 24-hour run. So
okay.
Some of us won't be available like this.
Because you're running 24 hours.
Yeah. We are running courses 24 hours.
So you take a break, a 2-hour break, and then you run double fast. No?
Yeah, but the finish is at 8 o'clock in the evening, so.
And which day is that?
Wednesday.
Which Wednesday?
Next Wednesday.
The 23rd.
Yeah.
So you prefer it to be the 24th?
Yes.
Yeah? All of you are running.
I'm not running, I didn't qualify, sir.
You want to cheer?
Yes, sir.
Yeah. That is kind of an event. I even acted once or twice. Because years we didn't win anything. But okay. So let's change that to 24.
October 24th, Thursday. Next month?
And 30 is okay. 30 is fine.
30.
Alright.
30 is okay. 30 of October. 30 of
Last week, or 2 weeks ago, rather, we stopped at discrete random variables, I think.
I don't think so. It's next. It's for November.
No, it's November.
We didn't understand the question. We didn't understand the question.
Yeah, I think so. Because the first session is in November.
Yeah.
It's on the 7th of November. 7th.
Okay, so also for I think some people asked about yes, who has already sent their project description to me? All right, who has received an answer? Okay, I need to do some more work, it seems. So I'll try to do that this weekend.
Is it to send by a mail or Toledo?
Please by mail. I don't look at the Toledo.
Oh, that's fine.
You upload it on Toledo. I'm supposed to find it there somewhere. Can you send it by mail? I think the instructions say by mail.
And so do all the group members have to send or just one?
Just one is fine. Please. I've forgotten that I already answered, you know. Just, I'll just answer 3 times. It may not be consistent, you know. One time I may like it, but, all right, so the people who have not sent it, there probably are some, because I don't think I received too many mails yet. Please send it as soon as possible. Who has not sent it yet? What was the issue? Oh, you don't Toledo. Okay. What is your issue?
I missed the first 2 lectures.
You missed the first two lectures, so you're.
I will send you later, probably.
You will do it by yourself, or you found someone.
I don't know. I don't know.
You don't know right now.
Yeah, because I don't think there's anyone who is available already on myself. Is that okay? Or I can join others?
You can join a group of two. Is there a group of two looking for? What's your specialty? This is now you have to sell yourself.
Electrical engineering or service design.
Circuit design, electrical engineering. So you're extremely smart, right? No, you're not. Okay. So a not so extremely smart person looking for.
Smart enough.
But smart enough anyway. Yes.
Well, it should be.
It should be, yes. Okay. So, but very good with computers and
A system?
systems
Yes.
and yeah. So who would like your name is?
Xiao
Chao Wang.
Yes.
All right. Chao Wang is looking for a group of two. Who feels like? So you can decide by yourself. So, but you can check with the other team member if it's okay. All right. And then you can see if the topic you like it as well, and the other group members. Okay. Anybody else who still needs to send their project? Yeah. So, what's happening with you guys?
Yeah, I'm ready already with my teammates who will check it. Was the deadline the 22nd?
I thought it was the 15th. What is it?
In the document it said 22nd.
Oh, okay. Then maybe there's some inconsistency in my documents. Okay, I think most people understood it to be the 15th because I received a number of emails on the 15th, so that kind of tells me this must be the deadline. Okay, so please send it. All right. Okay, so let's continue. So for the project as well, you have to, of course, work with variables, and we said that you had to have at least two continuous variables to help you do the response surface method, the optimization at the end. Yeah, so this is an issue for some of the groups anyway, to think of a response variable that you think may have some kind of optimum. Okay, so if you have something which is kind of if you keep increasing the time and you keep increasing the variable that keeps increasing, it's going to go keeps going. It's going to be difficult to do the last part of the project. So try to find something in the response variable which is has some type of optimum. Okay, if you can do that. So if you're clever, you can transform your response variable into something which may have an optimum. Okay. So yes, so some people have asked me, is time a discrete random variable? What do you think?
It depends on how you are controlling the time. Sometimes you can only control it by moving between intervals. So, for example, in a microwave, you can't control it. You have to, well, in the microwave I have, you can only go to 1 minute or 2 minutes or 3 minutes. You can't go in between.
Right. So what do you think? Is it a discrete random variable? Sometimes. On your microwave it is?
Yeah, it depends on the equipment. But if you have a timer, a clock, it's a continuous, well, like this in a cell phone, it's a continuous variable.
Right.
So it depends on how you are controlling it.
Okay. So, yeah. I would say it's a continuous random variable time, because you can at least imagine that you can determine the time in a continuous fashion. Maybe your equipment doesn't allow you to, but at least conceptually you can go. The example given here of something which is discrete is the number of defects. On a semiconductor, you cannot have half a defect. It's a defect or it's not a defect. So that's a discrete random variable. Okay. So you may have other examples then. number of persons in a group. You can't have half a person, so it goes by units of one. Okay, so that's, I would say, things like time, space, length, weight, they're continuous. If you have something like number of persons, defects, let your imagination work. Mine isn't working at this moment. That's discrete, okay? So that's hopefully clear then how that works. If we do discrete random variables, we don't have a PDF, a probability distribution function, but we have a probability mass function. So we indicate the probability of having this particular value. And that's also then at that point only defined, so it's not really a function. As we've seen it in the distribution function for continuous variables, but here it's like a also a discrete function, a function only defined at the values which are possible. So we call this a probability mass function, or PMF, as opposed to probability distribution function, or PDF, as we did last time for the continuous random variables. And so we have this function which is then defined at discrete points, and it gives us the probability of having that particular situation or that particular value. We can also make this into a cumulative distribution function, obviously. And instead of taking the integral of the function, we sum the values. Okay, so the probability of having the discrete random variable smaller than a certain value is then the sum of the probability values for all the discrete random variables which have a value smaller than this small x. Okay, so that's a cumulative distribution function. This is an example of such a cumulative distribution function. So of course it's a stepwise function. As you increase with the probability of having this value of 1, you increase there with the probability of having value 1, and so on and so forth. So I think that's all clear. So we're going fairly fast here. How do we calculate the average? Of course, we then sum the values of the discrete random variable times the probability of that, and that gives us the expected value of the discrete random variable, so that's the mean, and the variance is defined as given here. So the expected value of having the random variable minus mu, the mean squared. So there we once again do the sum of the differences squares, the difference between the discrete random variable and the mean squared times its probability. And the sum of that, of course, the square root of the variance is the standard deviation. And so this is a little example just to indicate how that would work. So we have 2 new product designs, and the marketing division has given its advice, and I think that's design A. They think they can make $3 million. Design B is not so clear to them. There's a probability of 0.3 that the revenue from B will be 7 million, and 0.7 probability that it will be only 2 million. Which design would you choose? Solution given here, X is the revenue from design A. There's no uncertainty, so we can say it's 3 million. All right. So the expected value in case design A is 3 million. In case of design B, we have to apply our rule to find the mean. So we multiply 7 million with 0.3 and 2 million with 0.7, so we get 3.5. And so we see that, of course, the expected value of design B is higher than that of design A. So we could go for design B. If you look at the means, the variability of course is larger in B. In A there's no variability, it's a fixed value. So we calculate the variability or the variance of design B is 5.25 million by doing 7 minus 3.5 squared and so on times the probability. And so our standard deviation would be 2.3 million. Okay. So then the question is, what would you decide to go with A or with B? Any idea? What will you choose? If you're the boss of the company?
I think it depends if we can afford to lose or not. If we cannot afford to lose, then we would choose the safer design.
Yeah. So if you cannot afford to lose, you should choose a safer design. Right. So say you're the CEO of the company and you get a bonus if your revenue is higher than the expected value.
But what happens to me if we lose?
Fired.
They get fired.
Only me or other people?
Oh, okay. Alright. You get fired.
Me?
Yeah.
Then I choose the riskier one.
You would choose a riskier one. Okay. You don't want to know how much your bonus is. Okay, so yes, it's not an easy. We could go on like this for some time. So it's not an easy choice, but I think you're right. It depends on how much risk you are willing to take, which way you go. All right. So let's look at some important discrete BMFs. So an important one is the binomial distribution. This maybe you have seen as well earlier times. So you have a trial. A typical trial is you flip a coin. You have two possible outcomes, heads or tails. And if you do that a number of times, you have what's called a Bernoulli trial. And if the trials are independent, so your flip, the way you flip is different, they're not related. Your different trials, for some reason, you can keep it independent, and the probability of success or having heads or tails is the same every time. Then we have this Bernoulli binomial distribution. So this binomial distribution, the probability you can write as such. So this is the binomial coefficient nx times p, p being the probability of having success on each trial to the power x. X, let's say what x, we have n repeated trials. So x, where does it say what x is? So x is a number of successful trials. So the probability of having x successful trials is given here. And so that's the binomial coefficient times p to the power x, 1 minus p, n minus x. Okay, so the binomial coefficient is not given here, but you know what it is, do you? Have you seen this before? Binomial coefficients. Somebody in the audience knows. Yes. like this. X factorial factorial. Okay, that's the binomial coefficient. All right, so you can then calculate this for a specific case. So this is n20. So a total of 20 trials. P is 0.5. So for a true coin, this would be the expected. So this would be the binomial distribution. Okay, so we expect 0 for 0 times heads, for instance. And if we look at 10, the probability of having 10 times heads is close to 0.18. If you change the probability of having a success on each of the trials to 0.1 or 0.9, this is what you get. Okay, so it becomes less, obviously less symmetrical. Okay. So if we have such a binomial random variable, our expected value, so the mean is n times p, and this is then the variance. So let's see if we can apply this. If we have a number of transmitted bits received in error, n equals 4 and p is 0.1, so then our expected value of a number of received errors would be 0.4, and the variance of the number of defective bits is then 4 times p times 1 minus p, so 4 times 0.1 times 0.9 is 0.36. Okay. Of course, you can see that the mean doesn't have to be on one of the possible values of the discrete random variable. Okay, so 0.4. We have 0, 1, 2, 3, or 4 as possibilities. So we get something which is in between 0 and 1. A second important distribution is the Poisson distribution. So when does that occur? If we have an interval of real numbers partitioned into subintervals of small length delta t, and assume that delta t tends to 0. And the probability of more than one event in a subinterval tends to 0. The probability of one event in a subinterval tends to lambda delta t divided by big T. And they're independent of each other. We have a Poisson process. I have to say that definition doesn't really help me too much to understand what it is, but say you have a number of raindrops falling on a car, for instance, at a moment when it's raining. That's a Poisson process. So you have discrete events which happen over a length of time. And so if you count that number of discrete events over a length of time, that is going to be Poisson distributed. And this is kind of important also in a lot of things we do as researchers, because a lot of the spectroscopy that we do has a Poisson distribution. And so if you have an analysis technique and you're shooting some type of radiation onto a sample, and you're measuring radiation coming off of the sample, that goes through a detector system. And so you're detecting the number of particles, for instance, which are coming into the detector, or the number of photons coming into the detector. So that's like the raindrops falling on a car. Okay, photons or electrons, protons falling onto a detector. And so it's important in that sense to understand a little bit about this distribution. Alright, so we have events occurring at random in an interval. And so such a Poisson random variable, the probability mass function is defined by this equation. And the mean and variance, the mean is this lambda, and the variance is also lambda. Okay. So if, for instance, we have a spectrum, and we have some type of spectrum. Say we're looking at, typically you make a spectrum by looking at, for instance, energy windows, and the spectrum consists actually of a number of counts in each of these windows, right? You've had enough of materials analysis to know this? Or am I talking gibberish? It's okay, yeah. So say for instance here you have your peak value, which is 100 counts. Okay. This 100 counts, that's lambda. So this is your best guess of the mean value is the value you have. Lambda is the expected value of x, right? So that's the mean, and the variance is also equal to lambda. So that means that the standard deviation is equal to the square root of lambda. Okay. So if you have 100 counts, that means that your relative error would be square root of 100 divided by 100, right? So this is sigma divided by mu, right? So if you have 100 counts, your standard deviation on that value is 10 counts, right? So you have a relative error of 10%, right? So this is what is called counting statistics. So how do we get this error to go down? Say we want 1% counting statistics error. You increase the counts. So if you want 1%, we increase it to what? 1% error, what do we need to do?
100 times.
You have to multiply with 100, so you need 10,000 counts. Okay. So how do you do 10,000 counts? So you have 100 counts, you think 10% is not enough, so how do you now you want 10,000 counts. So you have a machine, you're measuring, this peak is really important to you. Of course with 100 counts, it's so I'm kind of fooling you here. With 100 counts, your thing may look like this, you know.
Well, that experiment takes longer time.
Yeah, so you wait 100 times longer. So time times 100, okay? Your delta time. Okay, so say your experiment already took 1 week. get 100 counts. So now you have to wait. 100 weeks is about 2 years. So that's a long time. Say you're doing your master thesis. This is now out of scope normally for the master thesis. Even master students don't have that much patience. So what is it? What can you do?
The scan velocity.
Say again.
The scan velocity.
Get the scan velocity.
Yeah.
Okay. Say you have a technique where you're scanning. Okay.
Yeah.
Now you go faster with scanning.
Yeah.
So what does that mean? You're scanning over, for instance, the energy axis here.
Yeah.
So your time per energy window is actually going down. So if you increase your scan velocity, you will have less counts per energy window. Okay. So if you want to do this, you have to scan 100 times slower, basically. That's what we're saying. So if you want to increase the time, you go slower. So there's some other issue, some other ways to deal with it. Yeah.
Set up 100 machines.
Yeah, use 100 machines. Good idea. Yeah. Or have a source, which is an alternative. So have the intensity of the source times 100. So you can go to a different machine which has a higher intensity, or you could use the same machine or increase the efficiency of detection. So if you had a small detector, you increase the area of the detector with maybe 100. So there's a bunch of things you can do. Alright. So of course the easiest thing is to wait longer, but sometimes you don't have the time. And so people may go to places where there's a very bright source. Instead of using, for instance, a copper X-ray tube, they may go into a synchrotron where there's a million times more intensity or something. Okay, so then things go much faster. And the basic reason why you do that is because of this Poisson statistics. Because if you just have a peak of 100 counts, as we said, you have an error of 10%. So you want to have more reliability, especially as the information becomes important. You want to be sure that it's there. The peak. That's what you do. All right. So when looking at your data, doing your master thesis or something else, where you have this Poisson distribution, think about this counting statistics error and see if that needs to be improved to be able to make a more substantiated statement. Okay. So some examples of Poisson distribution. So this is lambda point 1, 2, and 5. So you see what is happening. As we increase lambda, of course, the probability of having a higher value becomes larger. An example of using such a Poisson distribution. So, for me not to speak too much, and I just wanted you to go through the example. It doesn't speak, which is
Elimination is a problem in manufacture of optical storage devices. So we have number of particles.
Yeah, so I use the PMF for the Poisson distribution. Okay. So on the small x
Is this? Yes.
in this Poisson distribution
Mm.
is 12 in this case, right? So you have 12 here and 12 there, 12 factorial, and 10 to the 12. And this minus 10 is, that's the lambda, which we calculated here. Yeah, as 10 particles. Right. Okay, so that's how that works. All right, we can also then determine the probability there's 0 particles occurring. And that's this here. 12 or fewer, then you have to sum. It's like a cumulative distribution function that we're using then now. So I think you can do this once you know what these different values and parameters in such a PMF are. So if we have a binomial random variable, we can approximate it as a continuous distribution. And this is done in this way. So if we have if we have this transformation here where z equals x minus np of the square root of np times 1 minus p, this z is then a standard normal random variable. So we can basically approximate a binomial random variable with this standard normal random variable this way. All right, so this is indicated here for p is 0.5 and 10 trials. Okay. So that works quite well if p is not too close to 0 and not too close to 1. So that allows us to then use a normal approximation to do calculations. So for instance, this is an example, transmission of bits, which we've done earlier. Now we want to see how well this works, this normal approximation. We have n equal to 50 bits, and the probability of an error is p is 0.1, and then the exact probability that 2 or fewer errors occur is then equal to this. You remember the binomial coefficients. We have 50n, this was x, and x has to be 2 or fewer, so we do this for 0, 1, and 2. And that gives us then 0.11. If we now do this based on a normal approximation, we do this transformation. And what do we have here? If we go back to this, so big X minus NP square root NP1 minus P. So this big X minus 5 square root of NP times 1 minus P, so N50 P.1, 1 minus P is 0.9, right? And so this has to be smaller than a certain value. And so we put here 2.5, why 2.5? Yeah.
It's a discrete random variable, so it doesn't matter if it's 2 or 2.5.
It doesn't matter if it's 2 or 2.5. Is that right? What do you think?
it matters because you go from a discontinuous variable to a continuous variable,
Yeah.
and the borders of your cell are go to a half to have the
Right, so if you look at this thing here, for instance, so you put this kind of histogram representation, so you're looking at something which is smaller than as something which is between two discrete values. So that makes sense to take half between 2 and 3, to have things which are smaller than 2. And so this is then the probability of having the standard normal variable z smaller than minus 1.18, and if you look this up into the table, that's 0.12, which is fairly close to 0.11. Okay. So that works pretty well. And you can do the same for a Poisson distribution as well. So then you divide by square root of lambda, and you subtract also the mean, so that you have the standard normal random variable. That kind of makes sense, because you want to subtract the mean and divide through the standard deviation. Okay. If we have more than one random variable and we want to do estimations of the probability of having a certain set of random variables, then the probability of having the random variables in a certain value range, if they're independent, is the product of the probabilities of having each of these random variables in that range of values. Okay, so that's something that is, of course, applies a lot of the times. So if you have independency of these random variables, there's something you can do. If you, for instance, problem here, we have a probability that a diameter meets specification was determined to be 0.919. What is the probability that 10 diameters all meet specifications? Okay, so the specifications are given here. This is an example we've done the last lecture. So this is the range that we need to be in. And so if we expect independence, then we can just use the product, and so we then do the probability to the power 10 to find the probability of having 10 diameters all meet specifications. Okay. So you see that the probability of having at least one diameter not according to specifications is already bigger than 0.5. All right, I think I will just skip this one here and go to functions of random variables. So this is a little bit about error propagation as well. So if you have also in your project you use a certain result, and you then do some type of operations on this result. Come up with your final result. What are then the standard errors after you've done all these operations? And so the way to do that is given here basically. So if you go from x to y by adding a constant, of course the expected value of the mean is increased with that constant, and the variance stays the same. So your standard error also stays the same. If you multiply with a constant, of course you multiply the mean, but the variance is now multiplied with the square of that constant. If you have then a linear function like this, obviously this would then be your expected value, so the mean, and also your variance you can calculate them through like this. All right. If you have normally distributed random variables and you calculate with those, and you have some type of linear function, then also the result of that is normally distributed and the variance is this. So this is exactly the same as the previous slide, but now random variables are randomly distributed. Okay. So important for you to realize that some of these rules work, and also when you make reports, it's important to think a little bit about what is the error I can expect, and don't just start putting numbers in your calculator into the computer and come up with 6 or 7 digits when you report on your data. Okay, so think about this and think about this error propagation type of rules. Okay, so an example of this. We have a manufactured part, length x1, width x2. They're normally and independently distributed. We have 2 centimeters as the first mean, and this is the standard deviation, 0.1 centimeter. Mu5 is 5 centimeters, and then the standard deviation is 0.2 centimeters. The mean and variance of the parameter. Okay. So this is 2x1 plus 2x2. So the expected value of this would be 14, right? So 2 times 2 plus 2 times 5 is 14. And the variance would be 0.2. Is that right? Would the variance be 0.2 square centimeters? Can you check? Is anybody willing to check if this is correct? What would you need to do to calculate the variance of this? Some people do this internally, other people start calculating. Yeah, so what do you get?
0.2.
0.2. And how do you do it?
Take the first sigma 1 squared times the coefficient in the y equation, and the same for the second one, and then you get 0.2.
Okay, so you did 0.1 squared times what?
2 squared.
Times 2 squared, so this is this coefficient. And the same for, this is mu2. It says now mu5, but this is makes more sense if this is mu2, so that you can use this for x2 here. So you do the same, and that gives 0.2. All right? And now we want to determine the probability that the parameter of the part exceeds 14.5 centimeters. As both of these are normally and independently distributed, we know that this y will also be normally distributed. So we can use now, once again, the normal distribution, and we want to use the normal standard normal distribution. So we calculate the probability of y being bigger than 14.5 is the probability of y minus the mean of y divided by the standard deviation of y, which if we then put this in, the value 14.5 minus 14 being the average of y, expected value of y, divided by the standard deviation on y, which would be the square root of this here. Okay. So that gives us then the z value, the limiting z value, for which we have to see what the probability is of z being higher than that value. And so if you look that up in the tables, that should be 0.13. Okay? So this is the probability then. All right? We have to be concerned with independency to be able to do this. So in principle, before you apply this, you should look at the correlation between the variables. So if there's a large correlation between some of these random variables, you cannot actually use these simple rules, and you have to make corrections for that. So then you have to use this covariances. So in case you're faced with such a case of not having independent variables, where you have a large correlation, then it's good to use this type of correction for the variance. If we have nonlinear functions, what you can do is then to calculate the expected value by filling in the mean. So you're transforming a mean by using, or you have some results which you transform by a nonlinear function. So then the expected value, of course, is putting that mean into that function, the nonlinear function. The variance you calculate by taking the derivative of the function to the variable, squaring that times the standard deviation of the original variable squared. Okay, so this is what you need to do. And so you have to look at how dependent that nonlinear function is on a change in the random variable and square that, and that gives you then the variance. Okay. So we have also an example on that one, and I'll allow somebody to walk us through it, as this is a good exercise. It saves my energy. Would you like to do it? Okay. Yeah. You would have also liked to do it, but
Power anticipated by resistance from an electrical circuit is given by 3.5 where I, the current is random variable.
so yes, I didn't say with the previous presenter,
Okay.
but yes, it's good to project your voice through the room. So that I was by accident watching a YouTube TED talk on presentations, and I was realizing that I made lots of mistakes. Making presentation, but one of the things is you have to project your voice. And this you do by also using your the chest, which allows you to project your voice. Alright, that's it.
Yes. Okay, where I, the current, is a random variable with mean 20 amperes and the standard deviation at 0.1 amperes. The resistance R is 80 ohms in constant. We want to find the approximate mean and standard the approximate variance of the power. This was given we have the derivative and we have the standard deviation. So we calculated through the formula, and that's 102,000 square watts. So that's a square watt. So to get the standard deviation, the root of that would be 220 watts. Yeah, at 20 amperes.
Okay. All right, thank you. So, of course, we have to take derivative with respect to the current, huh? Why is that?
Because it's separated.
Because, yes, and the current is a random variable, and so the resistance here is a constant, okay? So if we want to then apply the non-linear function rule, we need to, of course, take derivative with the random variable, which is the I, right? And then calculate this term. All right, so that's how to do it. This can be quite useful if you want to have an estimate of the standard deviation if you have a nonlinear function applied to your random variable. All right, so of course you can make this if you have a number of independent random variables and you take a function of that, you have to do the summation to get to the variance of the standard deviation squared times the partial derivative of the function to the random variables. Okay, so this is something you can certainly do. All right, let's have a 5 or 7 minute break.